Let me get everything pulled up and we'll get cooking. Okay, so we're gonna start right here and we're gonna talk about, we're gonna continue our conversation about factors that affect solutions. And so really we got into discussing gases last time. And so I think that's a good place to start here. So all right. Now, so just to recap, the first part that we discussed is structure. And the second and third part are temperature and pressure. I think that's fine. I hope everything got fixed. So pressure and temperature. All right. Now let me just pull up a couple of things here. I want to make a couple comments while we talk about this. So let's see. So you are. All right. So after. Okay. All right. So we said the first one it was structure, and with that we saw how polar versus non-polar is an important aspect to whether a compound will dissolve into a polar or non-polar solvent. All right, that was the first thing. So the second thing is dealing with temperature, and then the third thing deals with pressure. Now, temperature can affect both solids and gases. However, pressure will only affect gases. All right, so, and this is because solids and liquids are incompressible. All right. And gases are compressible. So that's important to make a note of here, just based off what we covered at the end of last lecture. So now to advance into this topic and to finish up the factors that affect solubility, we have to, look at gases a little bit closer. So gases are affected by both temperature and pressure. So first things first is let's look at temperature. All right, so recall, so let's say recall that the average kinetic energy is dependent on the Kelvin temperature. All right, so when we look at temperature has a direct effect on the solubility of a gas. Now, when I say direct, I'm not really talking about proportionality. I'm just saying that it has an effect on the solubility of a gas. So as we increase the temperature, the kinetic energy will also increase, and the molecular speeds of the gases will increase. As a direct result of this, solubility of a gas will decrease as the temperature increases. So this is an inverse proportionality. All right, so that's what we need to make a note of here about the the way the temperature affects the solubility of a gas. As you increase temperature, the speeds are going to increase, and if the speed increases, it's going to come out of the solution a lot quicker, so the solubility goes down. So our example is a soft drink. All right. Now you go to the store, you buy a soft drink. Now, when you buy a soft drink, you pull it off the shelf, it's hot. So one of the things I hate when I go to meetings and such, and they have drinks and stuff there, is if they don't get the drink cold before, if they don't put it in the refrigerator and cool it down, and they don't keep it cool, what'll happen is that as soon as you open that bottle, the flavor, the taste of that drink, whatever it might be, doesn't taste good. It's just not as good. So every time you go to a convenience store, if you want to buy, say, a cherry wine or Dr. Pepper or Pepsi, Mountain Dew, whatever the case is, your drinks are always going to be cold. And so there's a reason for them being cold, and that is that it helps to reduce the kinetic energy and causes the drink to be more stable. All right. And when I say more stable, we're talking about CO2. All right. So what makes a drink carbonated is the CO2 gas that is injected into it. To help with reducing the loss of gas from the drink, we put our sodas in the fridge and keep them cool. This action will increase the solubility of the gas due to the average kinetic energy of the gas molecules being lowered. All right. So that's the first thing, is understanding how the temperature will affect the solubility of a gas. Now the second thing is understanding how pressure will affect the solubility of a gas in a direct proportionality. All right. So as the pressure increases, the solubility of a gas will increase. All right. This is based off of Henry's law. All right. I'm gonna go back to the PowerPoint in just a second. So we'll look at what Henry's law states as soon as we get back to PowerPoint. But for now, we're just mentioning it. As soon as you guys get finished with jotting these notes down, please let me know in the chat box so I know when I can move on to the PowerPoint. All right, I'm going to move on here in just about a minute or so from now. So get done what you need to get done here, please, or take a picture. Thank you, Darius. All right, so I'm gonna move on here in about 30 seconds. So if there's something you did not get, please go ahead and take a picture of it, whatever you need to do. So that's a gas law, right, Hater? So when we talk about pressure and temperature, if I increase the pressure, I'm going to increase the temperature. If I decrease the pressure, I'm going to decrease the temperature. Pressure and temperature are directly related to each other. No problem. All right, so I'm going to go back to Henry's law. So go ahead and take a second here and write down the equation for Henry's law, and then I'll talk about it just a little bit more. Okay, so Henry's law, all it does is it describes how the solubility is related to the pressure of the gas. Now, K is a constant, and that constant is dependent on the gas itself. There's a table. I was going to show you this table in the textbook, but I want you guys to finish up writing this down first. So there is no video, so ignore that last point there. I'm just going to delete it. So there we go. You ain't gonna worry about it now. But the real discussion comes back into your soft drinks. Now I know that we've already talked about the temperature in the soft drink, but that also pertains to the pressure inside of a drink. So now when we talk about, when you first bring the soft drink out, or you get ready to open it, if you were to squeeze that bottle is going to be very, very tight. And it's tight because the companies themselves, they pressurize the bottles and the cans. they pressurize it so that way it forces the gases to stay dissolved into solution. And so that pressure is important. Now that pressure does not last forever. So those expiration dates that are on those drinks and those bottles are there for a reason. Your drinks will eventually lose the pressure because those gases will escape over time. They're small and they will escape through the cap at the top. So you over time, the solubility of your gases and there's or dissolved are going to go down. Now that's again that's back relating to Henry's law and stating that as you increase the partial pressure of a gas, you're going to increase its solubility. And so every gas again has its own size, its own interactions, and that all pertains to Henry's constants. Okay, so you have Henry's law constant K for the gas that's being studied. All right, so if we go and we look at the book and we find, let's see what page is it on. Let's see. Is it 581? See if I find it right fast here. Okay, here it is. So the table that's in your book doesn't list a lot of gases, but it lists enough just to get the point across that Henry's law of constant changes for the individual gas molecules that you see here. And that actually goes back to understanding the size and the molar mass. So, it goes back to that understanding that as the gas molecules become larger, their solubilities will increase. So, all this is directly related to each other. But in a nutshell, Henry's law is just as simple as just understanding that as the partial pressure of a gas increases, the solubility of that gas increases, and the more, and adding on to that, depending on the gas that's being studied, ultimately will affect the solubility of that gas. So bigger molecules are going to have greater solubilities for the just understanding that the intermolecular forces of attraction are greater for that of larger gas molecules. All right. So, so as the size and molar mass increase for a gas, its solubility will also increase proportionally. This is observed within Henry's law constants. What do you mean, Darius? You'd have to be given those. I would not ask you to solve for Henry's laws constants. I would give you those. Is that what you're referencing? Okay. Yeah, I would not ask you to solve for it. I would give those to you if I were to ask you to solve for it on the test. All right. Any other questions? All right. So we looked at how pressures affect what pressure and temperature are affecting gases. So what I want to do next is look at how temperature affects the solubility of a solid. All right. So that's the last thing we're going to look at here. No, not necessarily. I'll ask you how does it's a more of a conceptual problem than it is a calculation problem. You can calculate it, but that's more fun than just knowing what the differences are. So in other words, if I ask you how does the solubility affected by increasing the partial pressure of gas? You need to tell me that if the partial pressure of the gas increases, the solubility of that gas will also increase. That's what I want you to be able to do. All right, so how temperature affects the solubility of a solid. So temperature, again, is going to directly affect the solubility of a solid. Now, as the temperature increases, so does the solubility of the solid. Each individual solid, however, will have a different solubility curve. Okay. So that's where we're going to get to, is understanding how the solubility curve works. Now, we talked about it last night, and we talked about it fairly as much as I want to talk about it, but I'm going to at least go back over it for those that may have not been there last night. So solubility is again affected by the temperature change. And in this case, it's the opposite from what you see with the gas. So you have to be very, very careful when you are studying that you make a note of the difference between gases and solids. They follow their own set of rules, so you don't want to get them confused with each other. So make sure you keep a good tab on that. All right, so what I want to do is we're going to go back to the PowerPoint second here, and we're going to look at the solubility curve for a solid. Now, I drew this diagram, this graph up on the board yesterday, but I didn't talk about it a whole lot, but I talked about it about as much as I would like to talk about it. So, but I'm still, again, I'm gonna go over it here with you guys just to make sure we're on the same page. So what I want you to notice is that all these individual lines, these different colors, represent different solids. And the main pattern that you see is as the temperature increases, the solubility increases for that of a solid. All right, so that's just a shorthand writing there. Okay. So, however, there's one exception here, but we very rarely see anything like this. That is the bottom here. All right, so it's cerium sulfate. We don't really work with that particular compound, so it's not something we care too much about, but it's there. However, the other ones are a possibility of working with in the lab or at home. So sodium chloride, we talked about sodium chloride last night and how if you just look at the diagram here, I'm going to highlight this. So if you look at sodium chloride is almost flatline. Now, if we were to, talk about, let's see here, glucose. Now, glucose is not on here, but I'm just going to draw you what it would look like. All right, so I didn't really go backwards, but that's kind of how it looks. I showed you this last night. So if we compare glucose with that of NaCl, what we see is the NaCl stagnates. All right, see NaCl, not a whole lot can dissolve in the solution. So no matter how high the temperature is, the solubility of NaCl does not change very much. So its saturation point stays fairly constant the whole way through the temperature change, the temperature range. But when you look at the solubility for glucose, which is this highlighted red line here, that has a drastic change. And so once you get right up around 50 and higher, the solubility of sugar becomes infinite, meaning that if you boil water and if you wanted this much sugar, you could put a 5-pound bag of sugar in and it would completely dissolve in the solution. Whereas if you were to put NaCl in, Well, only 40 grams of NaCl is going to dissolve for 100 grams, where so there is not an infinite amount of NaCl, there is a finite amount. And so each of these salts have their own individual solubility curves. And that's something you're going to be working on in your personal project. And you are personally going to try to figure out, how soluble these salts are and and what the solubility curves might look like. You don't have to do that, like these curves are, but it's just a general figure of speech. You're going to play the same rules that we're talking about here. So now, as you look at the y-axis, we talked about NaCl at that 100-degree mark having 40 grams of NaCl for every 100 grams of water. So if you know the mass of water that you're going to use, let's say we're going to use 600 grams of water. Well, the question would be, how many grams of NaCl would you use or could you put in there? So now the difference there is 6 times. So we would do 40 times 6, which means that you could dissolve 240 grams of NaCl for every 600 grams of water. It doesn't change just because you add more water, doesn't necessarily mean the solubility changes. It just means that you can put a little bit more in because the saturation point is still the 40 grams per 100 grams. So, so these lines, yet again, represent the saturation points for the salts that are on the here, all right, that are on this. And you could go on to Google and you could actually look up all the solubility curves for all different types of salts and compounds. But for right now, we're just going to keep it simple, and have a little glance at this solubility curve here. So that's all you need to do with the solubility curve is understand that this solubility curve represents that for solids. There is a solubility curve for gases, and gases have the opposite trend. We've already talked about temperature and gases. So as you increase the temperature, you decrease the solubility of a gas. All right. We've already talked about that. But what you also need to make a note of is that as you look at these molecules here, these molecules really hinge around the molar masses, uh, with the exception of helium. Of course, helium is an oddball. We don't really typically use helium unless we have a balloon we're filling up, something like that, but that's something different here. So, but the main point is that as the temperature increases, the solubility for all of those gases decrease. All right. So that's all we're going to do there. That finishes up that section that deals with the solubility of and factors that affect solubility with both solids and gases and liquids. All right, we have to keep in mind that there was a topic about structure. All right. So let's just look at. So this is the starter problem. This is something that we were in class. We were starting a class. I throw this up on the board, so we can work this out. So what I want to do is let's just pick a couple. So say we take this one here, and we take this molecule here. So C7H16 is carbon hydrogen. If you draw this out, it's very, very nonpolar because it's all hydrocarbon. So would the C7H16 dissolve better in the CCl4, which is nonpolar, or water, which is polar? Right. So good. Thank you guys for answering. All right. So it dissolves into CCl4 because of its nonpolar nature. All right. So now let's look at HCl. All right. HCl. All right. Going back to just the Lewis structure here. HCl has a dipole, meaning that HCl is polar. Well, HCl, since it's polar, will dissolve into H2O because H2O is also polar. Remember that we talked about polar dissolves polar and nonpolar dissolves nonpolar. All right. And we've already looked at these in the last topic, so we're gonna move on. All right. So now we're gonna get into a new section for this chapter, and that is ways of expressing concentrations of solutions. So what I'm actually going to do is I'm just going to go through, we're going to look at the different units of concentration, and then we'll work some examples. All right. So and I want to make a note also that it would be a good idea if you have this, so to go ahead and pull this out. This is your guide to solutions, and this is the section that we're in right now. All right. So we're going back here, and the first one we're going to look at is molarity. So molarity is expressed as moles of solute per liter of solution. Now you need to make sure that when you write this down, that you write it down exactly the way you see it. Moles of solute per liter of solution. There's a reason. Because you don't want to just say moles per liter. That's what you learn in chemistry 1 is moles per liter. But there are missing links here that you got to be careful with. And that's the units that are present. So moles of solute per liter solution. All right. Now, molarity is something that we've already looked at and we've discussed. And I say I'm talking about in general chemistry 1, but it's not something that we would use all the time. Now, the second bullet point here is a super important point, because what we have to understand is that volume and temperature are going to be affected by each other. All right. Now, so as we talk about temperature, so if I increase the temperature, what will happen is the molecules are going to move faster. And as a result, the volume of that solution will also go up, and vice versa as the temperature goes down. Think about your skin. If you wear a ring in the summertime, it fits a lot tighter than in the wintertime. And that's because your hands are made up of mostly a solution, and they will swell because the heat causes them to go up, increase in size. In the wintertime, it's cold, so your fingers shrink because the volume of your hand shrinks in the winter. So molarity is a good, and it is an important unit of concentration, but it's not the best unit in some cases. All right, we'll talk about what that case is later today. And so for now, just make sure you have this wrote down. All right. So the second one is mass percent. All right. So mass percent, A represents anything. All right. So you could determine the mass percent of anything using this same equation. So it doesn't necessarily have to pertain to something that we do in chemistry class or in the lab. It could pertain to something we do outside. So yeah, so if anybody ever goes into a hospital and you look at the IV bags, the IV bags are 0.9% volume over volume. All right, so V over V is what they would express it. So this is a percent volume, but it's the same as percent mass. It's just determined by volume instead of mass. But again, it's a percentage, and all percentages are out of 100. You take the mass of whatever part you're looking at, and you divide it by the total mass of that solution. And that's something you have to be given as it is. So it's not something that you can just predict on your own. You have to be given that information. So in a second here, we're going to switch the slide and we'll look at an example. Are there any questions before I go on? Okay. All right. So let's move on then. Okay. So this is a really good problem. All right. This problem here. Uh-oh. Pull this down here. Okay, good. All right. So this problem is an old exam question of mine. And this actually pertains to something that we really have to pay attention to in the lab. When y'all go in the lab and you get your bottles or your beakers, on these bottles and on these beakers, you're going to have these numbers and then the compound that's present. All right. So in this case here, in this beaker, you'd have 0.1 molar NaCl. And what that means is you have 0.1 moles of NaCl for every liter of solution. All right. I abbreviate solution as this here. So you'll see me write it that way quite a bit now. All right. Now, so if I were to, work with another compound, say HCl, oftentimes now if I go and make this solution here, all I would have to do is figure out how much mass of NaCl to put into the water. That's not always easy. So when we go into the lab in the stock room, and I know y'all do not go in the stock room, they have these bottles in there, and in these bottles you have what are called stock solutions, and these stock solutions are basically concentrations that are extremely high. Now, in order for us to figure out what the molarity might be in that stock solution, there's a couple things that we have to know. Now, in this problem up here, we're given the percent mass of ammonia, and then we're also given the density. Now, the question is, what is the molarity of NH3 that would be inside of this stock solution? All right, so this stock solution here is composed of NH3, but we don't know what the molarity is for that solution. Now, so there's a play of units. There's a play of the way we set it up. All right. So when you're working a problem like this, you have to be very careful in understanding what each part really represents. All right. So the density of this really represents the density of the solution. All right. That means in the solution, you have 1.165 grams of solution per milliliter of solution. And so we use that to help us go through conversion. All right. So I'm going to pull up some chicken scratch here. All right. So here we're going to utilize this density as a conversion factor. All right. Now, the next thing we're going to do is we're going to take the percent mass. All right. So we use the percent mass and density to solve for the molarity of the NH3. So you have to have both present. If you're missing the density, if you're missing the percent mass, you can't do this problem. At that point, you're at a stalemate and there's nothing you can do. All right. So what I want you to do is I want you to pay attention to the first part. And I'm just going to box this in here. All right. The percent mass is out of 100. So what you do is that you assume out of 100 grams. All right. Now, this is out of 100 grams of solution because we're talking about the percent mass of the solution. So when I write this out as a conversion, I take the 28 grams of NH3 and I divide it by 100 grams of solution. Now, when I do this, notice that when you divide out by 100, you're actually taking out the percentage of that percent mass. So that's a plus in our case. But it also is helping us to cancel out the unit that we find in our density. So when we take the percent mass divided by 100 and then we multiply it by the 1.165, what that does, it starts to help us to get our units where it needs to be. So the grams of solution are going to cancel out here. Now, the second part, and I'm saying the second part, so when we get here, the second part is now, so up on the top portion of the percent mass, when you assume it's out of 100, that means that you have 28 grams of NH3. So remember back to the fact that the roadmap is grams to moles. And so to go from grams to moles, you're going to divide by the molar mass. Now, the molar mass of NH3 is 17 grams per mole. So what we would do is we would take the 28 divided by 100. All right, so 28 divided by 100 times the 1.165. And then since we're dividing it by the molar mass, we're going to divide it by 17 grams per mole. So right now, our first step was using the density. Our second step was using the molar mass. And then our last step is where we have to understand the units for molarity. Now they're asking for molarity. So remember that molarity is moles of solute per liter of solution. Now, in the density, you have the grams per milliliter. So what we're going to do is in our last step here is we're going to multiply by 100, or actually 1,000 here. So that way we get our unit out from the milliliters and back into liters. So your final answer, which I want you to go ahead and calculate, is going to be a moles per liter, which is what units we're looking for here. All right. So you get 19.2 molar for your answer here. All right, so you get 19.2. And let's see. So down the bottom right hand side, I'll write out the whole thing. So 19.2 molar NH3 is the answer there. Any questions on that? I was trying to find the old textbook problems, but I can't find it. I'm going to send you guys something in just a second. So get your, as soon as I get logged in here. This is not, this is a different website, but so don't worry about what the website is and where it is found. You won't be able to get to it. I'm not sure if this is online or not, but if it ain't, it's going to be given to you in just a second here. Yeah. Okay, here it is. All right, so go ahead and pull that down here. All right, so everyone look at your chat box, please. Yeah, that's correct, Amy. So I'm going to give you this handout. Might be something we can work on next week. I need to, let me get this to everyone here. Let me see here. All right, so check the chat box here. Okay, it says it was sent successfully. Download that practice problem set there. And well, I'm going to go ahead and I'm not going to give you the answers to that yet. So you say, well, you might be wondering, well, what problems should I work? So I'm going to tell you that right now here. All right, so problems 35 through 53. So 35 through 53. So those are the problems that you should work. Now, I'm going to expect you to work these, but I'm not going to take these up for a grade. All right, because I want you to practice with these and I don't want you to feel stressed out with this. But if you don't work these, that's your problem. It's not mine, because if it comes to the test and you don't know what you're doing, that's your problem. I don't want to be the person that gets pointed back, say, oh, you didn't give me enough to do. If you work all these, you should be fine on any question I give you on a test. As long as you understand what you're doing. If you're just doing it just to do it and then not learn from it, then that's a different problem. So you all should work these problems and work them to the point where you understand what you're doing and why you're doing it. All right. That way it makes things easier. Now, one of the questions on this, so looking back at this problem here and then looking at the worksheet itself, so problem 51 and 52 actually revolve around this type of problem. I'll get it to you guys here in a few minutes, okay? Stephanie. All right. So again, 51 and 52 are direct examples. Well, one is direct and the other one's indirect. Either way, they're both examples of what we have done in this problem set here, right here. Okay. Now I want to go ahead and get into the next unit. Okay. So the next concentration is parts per million, parts per billion. Go ahead and take a couple minutes, jot this down, and then we'll go over it. Yes, I will post answers next Monday, Tuesday-ish time frames. I want to give y'all a chance to work on it on your own. Okay. So that's something y'all can do this weekend. Work on that worksheet. Good practice. I have not posted it yet. Where did I send what to, Kayla? I sent that solutions practice problems to everyone, if that's what you're referring to. No, it should be in your chat box. Kayla, you should be able to scroll up and find it and to download from your chat box, assuming that you're on a computer where you can download it. If not, you can just send me an email. I'll send it to you that way. go ahead. I'm gonna go ahead and get this where y'all can have this. All right, thanks. Okay. Okay, so as you guys are jotting this down here, I want to make sure you understand that ppm and ppb. All right, these are both units that are expressed for very small concentrations. All right, so this is for very small concentrations. Now, molarity is a unit that we use just in the laboratory. Molarity is typically in a concentration unit that's fairly high, but parts per million, parts per billion are much lower in concentration. So if you get if you were to calculate and you were to calculate, let's say 0.0000015 molar, well, that may not be the best way to express the concentration because it's a very, very small concentration. You can do it, you can use millimolar. All right, millimolar is just where you move the decimal place 3 places over. That'd be 0.015 millimolar. Now, yeah, that's expressing a smaller concentration, but still it's a small number. So it may not be your best choice. So parts per million, parts per billion are used for expressing concentrations that are very low in number. So now I want you to think about this. So let's say we do a problem, and in that problem, we determined that you have 2.5 parts per million of zinc ions in the solution. So now what exactly does this mean? Well, what it means is that if you were to sit there and you were to count a million of those particles that go by, out of those million particles, you're only going to have 2.5 zinc molecules or zinc ions. So the fact is that that number is extremely small. So when we talk about a needle in a haystack, this is really what we're looking at. It's a needle and haystacks, very, very small. Now parts per billion is 1,000 times smaller than parts per million. And so if you look at the exponent here, it's times 10 to the ninth versus times 10 to the sixth. So parts per billion would be a much smaller unit of concentration. Now, so if we were to take this parts per million for zinc and we would convert it into parts per billion, we would just move the decimal place over 3 places to the right, which would be 2,500 parts per billion of zinc ions. Now, it sounds like a lot because 2,500 is a lot, but we're taking it out of a billion particles that go by. So if you were to count a billion particles, only 2,500 represent zinc. So still a very small number. And so that's why parts per billion and parts per million are useful when we're expressing small concentrations. So now in the real world, we would use this to when we talk about discussing the toxicity of certain metals in human bodies or in a rat, basically. So we call that LD50. All right. So if I were to go on the Google, we'll do this right now. This is a good little exercise. So I don't know why I'm Googling this right here. So the LD50 of let's see what caffeine is. That was a top hit. So LD50. All right. So let's see. Do they have it in parts per million? I don't see it. It's not much. So if we take a milligram, so 192 milligrams, so that's only 0.192 grams per kilogram. So a kilogram is roughly 2.5 pounds. So all it takes is a smidgen of caffeine to reach the LD50. 50 is half the amount that it would take to become toxic for you. So you can take too much caffeine, and it could potentially harm you than to help you out. So those Monster energy drinks, those NOS energy drinks, they're very bad for you because they produce a lot of caffeine in a short time span in relation to the size of the drinks that you drink. So they make you go real fast, but then about 4 hours you'll crash out and you can't do it. You have to take another one to keep going. So again, we like to express these concentrations in parts per million and parts per billion. And in fact, this milligram, if we were, this is really relating back to that, even though they don't say it in the sense that what we're talking about here, it's still related to parts per million. All right. So, all right, so let's keep going here. All right, so that's parts per million, parts per billion. If we look back at the guide to solution, all right, we come down here. I do have an example for you to look at, so you can always reference the guide for examples, since we don't really do as many as we have time. I wish I could do bunches of examples with y'all, but we just don't have the time that's necessary. So that's what we'll do next week on Tuesdays. We'll do more problems like this. So a solution contains 54 milligrams of copper and 543 grams of solution. Determine the concentration of copper ions in parts per million. So notice that they take the mass of the copper here, which is 54 milligrams. And I say I did this for you. So I convert the milligrams into grams, and then I convert, all right, so I take the grams of solution and put it at the bottom, divide them in each other, multiply it 10 to 6, and you end up with parts per million. Now, if we go back and we look at this here, we can see that we have milligrams per kilogram. So what we want to do is we could figure out the ppm, and we could take the milligrams, convert it into grams, and then convert the kilogram into grams as well, and then divide them out, multiply 10 to 6. I don't even know what that would be. I'm actually interested in what that would be now. You got me working on it. So what is that? So that's going to be what, 0.192 divided by 1,000 times 1 times 10 to the 6th. That gives me 192 parts per million. So I just calculated it in parts per million. So again, all I did was take the milligrams and convert it into grams. And I took this kilogram because it says per kilogram, and I converted that into grams, which is 1,000. So you take 0.192 divided by 1,000, and then multiply that by 1 times 10 to the 6th, and you get 192 parts per million for your answer. So that means that in this concentration, it doesn't take a lot to reach that LD50, and that's 50% of the lethal dose that a human being, or in this case a rat, could take. So and you can see right here it's 57 milligrams per kilogram, have been fatal as well. So if we were to multiply this by 2, so a human body, if you were to consume 384 parts per million of caffeine in your body, it would kill you. So yeah, it don't take a lot. So when they put caffeine in your coffee or your soft drinks, or in the NOS energy drinks, they can't put a lot in there because it could cause you harm. Goody powders are very bad for you. They're only good for when you have really bad headaches or a lot of pain, but they're really bad because the caffeine in a goody powder is pretty high. And I take goody powders once a blue moon to relieve myself of a headache if I get a migraine. And I can tell you, I can feel my heart racing when I take those because of how much caffeine that they put in there. I don't know if you guys take goody powders or not, but it's that they're good for pain, but they're bad for your health. So, all right, let's keep going here. All right, so we have 2 others I want to cover here tonight, and that's mole fraction and then molality. So I'm going to just let you jot this down here. So mole fraction, please write this down. I'm going to switch the slide in a minute. We're going to get to molality. Then we're going to go back to the guide to solutions. So, all right. All right, so it's mole fraction. And we did mole fraction in the gas chapter, so this is nothing new. But we'll talk more about how we're going to use mole fraction when we get into colligative properties. So let's do molality now. So go ahead and jot down molality, please. So what does molality sound like to you guys? What are the concentration does molality sound like? Yeah, that's right. It's molarity. Kayla, you're being awful quiet tonight. That's okay. Not much to say. Good deal. That's fine. Not a problem. All right. And so what I want you to pay attention, put a little star beside this one here. Molarity changes in relation to the temperature because of volume, but molality does not change because mass does not change in relation to temperature. So molality is a better unit of concentration to use than molarity. Although we don't use molality very much, we use molarity because a lot of our solutions are made up of in the water. So they're aqueous based. But again, we're going to use molality when we get into colligative properties. So, and that is the next thing we're going to get into. So the last thing I'll let you jot down here is changing molarity to molality. This is a flow chart. I actually think you should take a picture of this versus writing it down. You can write it down later. So I think taking a picture of that would be the best option here, or just pull it off with a PowerPoint from Canvas and then print it off. So a flow chart is going to help you with the roadmaps and how to go from point A to point B. All right. We've already done an example tonight where we took the mass percent and the density and we went forward to calculate the molarity. You can take the molarity and the mass percent and go backwards to figure out the density or vice versa. So, you know, these conversion factors that we're using can be utilized in both directions. So this flow chart helps us to see that. All right. So that's the last slide we're going to look at here. Now, I want to go back to the guide here. All right. So in the guide, let's see. Okay, I'm in the book. Sorry. Let me find the guide. There it is. So in the guide, I work out several examples for you. So I would reference you to go ahead and look at these examples and to make sure you work them. All right, I'll give you two examples here. I'll give you one that involves copper up here, and then another one that gives you that involves the use of ethanol. All right, and then I'll give you some practice problems. So there's a good chance that we'll be using this in the problem session next Tuesday, and we'll work some of these practice problems out along with some of the questions from the old textbook problems. So I would highly recommend you spend this weekend working on concentration units and making sure that you have a good grasp of them. Now, the last thing I'm gonna mention to you tonight is that you have this other unit that was not stated in the PowerPoint. All right. So I did put a link here, and this link discusses normality. Normality is an old school concentration unit, and we very rarely use that in chemistry now. But if you were to go over to Europe or somewhere like that, they possibly you could see it there. I will not be testing you at all on normality. I'm not going to say anything else about it other than the fact that if you are interested in this unit, you could go to this link that I provide you and you could read a little bit more about how normality is related to molarity. All right. And so that's where we're going to leave it. So that's all. That's where I'm going to stop tonight. I think that's a good place to stop. What we're going to do on Monday is we're going to start here with colligative properties. So again, work on those worksheets, those problem sets that I gave you, work on the practice problems, and do as many examples as you can do and as you have time to do. All right. The more practice you do, the better you get at it. All right. So I'm going to stick around for a few minutes like normal. If you guys have any questions, feel free to ask me. If not, y'all have a great weekend.